The ideal gas law. Today we're going to cover the ideal gas law, exactly what an ideal gas is, and some of the strategies you can use to solve physics problems. The ideal gas law comes to us from a period of rapid technological change that we call the Industrial Revolution. A lot of the advances that we have, for instance, Newtonian physics, we associate with Isaac Newton. Um, the ideal gas law is not the same way. During the Industrial Revolution, we were developing steam engines, water wheels, combustion, and there was a real need within industry and within the economy to understand how these processes worked. A lot of different people were able to contribute to these. So rather than driving later economic growth, in this particular case, physics was being driven by an economic need. Now, this doesn't happen again until, say, the Manhattan Project during World War II, or even the advances in solid state physics that happened uh, in the latter half of the 20th century. Well, one of the relationships they came up with was called Charles' law. Okay, so this is a relationship between volume and temperature. That volume is proportional to temperature under the conditions of constant pressure. In other words, the ratio of volume to temperature is equal to some constant. If we were to graph volume versus temperature, we'd end up with a nice straight linear line. The slope of that line is, of course, the constant K that we would see in the relationship off to the left. We can use this to solve problems under conditions of constant pressure, yet again. We take the ratio of volume to temperature at, say, time 1. Since that's equal to a constant, it'll be the same constant for some later time. We can compare those two ratios for two different times. If in fact we only have one unknown at this particular point, we can solve for that unknown. Boyle's law. A gentleman named Boyle noticed that pressure is inversely proportional to volume under conditions of constant temperature. We're going to call that an isotherm. These are isothermic conditions. This means that the product of pressure and volume is equal to some constant. Okay, this is a very different line. This is a very different graph than the linear graph that we had for temperature and volume. But it's still very predictable, and we would call the shape of this curve an isotherm. This is simply a 1 over x. If you were to graph 1 over x, for instance, you would get this same shape. We can take the product of pressure and volume at time 1 and compare that again to pressure and volume at time 2. As long as we're at the same temperature, the product will remain the same. We can also relate pressure and temperature under conditions of constant volume. So pressure divided by temperature, the ratio of pressure to temperature is a constant, and we have a familiar linear graph here. Again, we have the same sort of ratio that we had for volume and temperature. And lastly, we can combine these into the combined gas law. Pressure times volume divided by temperature is, of course, some constant. And again, with a matching ratio relationship. In the objectives of this lab, you're going to state the relationship between the average kinetic energy and the temperature for a sample of gas. You're also going to state the relationship between pressure and volume under conditions of constant temperature. Well, we already covered that one. That was Boyle's law. You're going to solve problems with the combined gas law with at least one of the variables, pressure, volume, or temperature, held constant. Those would be under your ratio expressions. The first one we have to come back to. State the relationship between the average kinetic energy of the temperature of a sample of gas. The kinetic energy of gases. The ideal gas models, like many of the other models that you've run into in physics, we're going to create a simplified version of the real system in order to be able to make predictions and to understand complex phenomena. Some of these assumptions that we're going to make is that there are negligible forces acting between the molecules. In other words, we have a sample of hydrogen or helium, or oxygen and nitrogen, for instance, the gas you're breathing, we assume that particles which have some separation between them are not attracting or interacting in any fashion. That's a pretty close approximation to the real situation. That molecules occupy a negligible volume with large separations. This is also a pretty good assumption. The molecules are very, very small compared to the volumes that they occupy. The molecules behave as rigid spheres undergoing perfectly elastic collisions. In other words, no kinetic energy is lost. Indeed, no kinetic energy is lost. Whether or not they're rigid spheres or perhaps two rigid spheres attached to one another is slightly different assumption, but it'll work out for the most part. We're going to also assume that pressure is the result of collisions with the walls of the container. This one's easy enough to understand. You can imagine taking a fire hose and spraying it against a pressure plate, and you can imagine that the particles of water, the individual molecules of water, all moving in mass, striking against that pressure plate, are going to exert a force. That one's not hard to understand. This last one, the temperature of the gas is proportional to the average kinetic energy of the molecules. That one's going to require a little exploration. So the ideal gas is related to the temperature. It relates the temperature to the kinetic energy. For a molecule like helium, the average kinetic energy is equal to 3/2 times the constant K sub E, also called Boltzmann's constant, times the temperature. Now, Boltzmann's constant is just a constant that relates temperature and energy. Okay. It's convenient to work with entire collections of molecules, and so instead of working with, say, a single molecule like helium, we're going to work with collections of molecules measured in moles. Now, moles is the small n that we see below us, and your Boltzmann's constant is going to change into something called the gas constant. So the ideal gas law is pressure times volume equals the number of moles times the gas constant times temperature. Let's go into a little bit about what these variables are. P is pressure. Pressure is the force exerted by the gas per unit area on the walls of the container. It's measured in pascals. In other words, newtons per meter squared. You can remember that by a small joke. Okay, Einstein, Newton, and Pascal were out on a picnic one day. They decided to play hide and seek. Pascal runs for the hills. Einstein is it. Newton simply stands there and draws a square around himself. Einstein opens up his eyes and says, "Ah, Newton, I have found you." And Newton says, "No, you have found Newton over a square meter. You have found Pascal." Okay, so it's a stupid joke, but you'll remember the units. Take care with the units. Sometimes you'll be given pressures in units of kilopascals. You'll need to convert that to pascals. Remember, the 1 atmosphere is 101,000 pascals. Make sure you convert that to pascals or newtons per meter squared before using the ideal gas law. We can also speak of pressure as an energy density. If we take this newtons per meter squared, remember the silly joke that I gave you, okay, and we multiply it top and bottom by units of meters. We have Newton meters on top, which is energy, it's a joule, and underneath we have meters cubed. In other words, we have joules per meter cubed. In other words, it's an energy density. Okay. Volume is the SI unit of volume is going to be meters cubed, not centimeters cubed or millimeters cubed. You're going to need to convert those back to meters cubed before you begin working with it. It's very easy to make mistakes with these if you don't make those conversions. The conversion from meters cubed to centimeters is 10 to the 6. 1 meter cubed equals 10 to the 6 centimeters cubed. The conversion between 1 meter cubed and millimeters cubed is 10 to the 9 millimeters cubed. 1 meter cubed equals 10 to the 9 millimeters cubed. If you end up with a non-physical answer that's off by, say, 10 to the third, 10 to the sixth, or even 10 to the ninth, take a look at the units of the volume. That would be a good place to check if you run into an error there. The number of moles. The value of N is either given to you in the problem statement, or if you have the number of molecules itself, large N, capital N, we would find that by taking large N and dividing it by Avogadro's number. So the number of moles is the number of particles divided by Avogadro's number. If you don't have Avogadro's number memorized at this point, go ahead and just take 5 minutes and copy it over and over and just get that out of the way. The gas constant. The SI value for the gas constant is some value that you can look up and nobody bothers to memorize. Notice that the units are joules per Kelvin per mole. So that already tells you what units your temperature are going to be in. Okay, remember the other side, pressure times volume. Pressure times volume was an energy per unit volume. We're going to multiply that by a volume. So in the ideal gas law, the left-hand side is in units of energy. You can see over here that the gas constant is also going to cause the right side of the equation to have units of energy, which is what you would expect. Okay, so these are SI units. You can still look up the gas constant in other unit systems. The numerical part of R will change along with these units. The temperature has to be in Kelvin. To convert temperatures given in degrees Celsius to Kelvin, just add 272.15 to the Celsius value. 1 Kelvin, we don't say degree Kelvin, 1 Kelvin is equal to 1 degree Celsius. So one of the consequences, though, is even though I caution you to always use the Kelvin scale, if you're ever working with a difference in temperature, Celsius will still give you the right answer, as long as you're working with a difference. But to be safe, I recommend that you always convert to Kelvin. Well, let's take a look at a gas with two different species of molecule. Now, the mixtures of these molecules, let's say we have a mixture of hydrogen and helium. Okay, because they're mixed together, they're going to have the same temperature, and thus the same average kinetic energy. The kinetic energy of the hydrogen is going to be equal to the average kinetic energy of the helium. We're going to express the kinetic energy in terms of 1/2 mass times velocity squared for both species. So mass 1, velocity 1 corresponds to the hydrogen. Mass 2, velocity 2 corresponds to the helium. Let's go ahead and cancel some like terms there. And we're going to recognize that mass 2 is just 4 times the mass of the hydrogen. And we're going to go ahead and cancel another like value here. And we see that we have perfect square on both sides. We see that the average velocity of the hydrogen is going to be twice the average velocity of the helium. So just because we have the same temperature and the same kinetic energy, it doesn't mean that there's no expressible difference between the behavior of the gases. As a matter of fact, we can talk about this phenomenon called atmospheric escape. The Earth loses all of its hydrogen. And in fact, it loses all of its helium as well. If you have a helium balloon, you pop that helium balloon, that helium is going to rise into the upper atmosphere and is simply going to escape. We're simply going to lose it. The Earth's gravity is simply not strong enough to hold on to hydrogen and helium. They're at any reasonable temperature, their average velocity is going to lead to the faster of the molecules exceeding the escape velocity of the Earth, and they're simply going to escape little by little. Heavier molecules, like say diatomic oxygen, diatomic nitrogen, and CO2, those are going to hang around. Those have more mass. And so they're going to move slower, and they're going to be much further away from the escape velocity of the planet. Okay, and so that's something that you can help to understand. Another thing that you're going to do in the lab is you're going to take a look at two different species of molecule, and you're going to ask yourself, what happens is one particular species more likely to escape a closed container than another species. And the only real difference between them is going to be mass. And this should help you answer that question. If you'd like to know more, I would suggest Chapter 12 of Rex and Wolfson, Essential College Physics, Addison Wesley, first edition, November 1st, 2009, or any ideal gas law chapter of any college physics textbook. I hope you enjoyed the video, and I hope it was of some assistance to you.